equation at parabolic and umbilical points for two-parameter families of surface.
Okay, thanks for introducing me, Federico. And I would like to thank the organizers for accepting my work, for the opportunity, for great parties, so nice parties. And also, I need to say, Feliz cumpleaños. This photo was in workshop in Brazil, in São Carlos, in 2012. It's the first time I meet you, because this, also I am in this photo, but I only want to focus on you, of course, okay?
Those switches we got.
Yeah, switch is there, and your leg heavy Masaki, okay? Let's go, let's talk about my presentations, okay? So, this work is one continuation of our work classification of jet of surface in projective 3 space via central projection. This works, we classify the germs of a surface given by for Monge form, and we classify one parameter families of surface and two parameter families of surface, but using projective transformations, okay? So, one consequence of this paper, we talk about binary differential equations about this classification, exactly at parabolic and umbilical points for two parameter families of surface, okay? Here, more specifically, we try present some examples of parabolic and flat nodal curves and study the bifurcation of that guys for two parameter families of surface. This work is with Yutaro Kabata, but Yutaro is not here, and Toru Omoto, okay? Toru Omoto da Hokkaido University, Yutaro agora, oh, sorry. Yutaro is in Kobe University, Toru Omoto in Hokkaido University, okay? So, for explain a little bit about the first work, we using a key singularities of central projection of surface to classify the Monge forms of given by of the surface by projective transformations, okay? There, using the singularities of central projection, it's possible we classify the Monge form of the surface, okay? So, but interesting things happens interesting things happens here when the viewpoint of the central projections on asymptotic lines. So, it's possible we study asymptotic lines using binary differential equations. Okay, don't work. Yes, using asymptotic BDE, okay? Look, the asymptotic BDE is given by this equation and using the normal form of the surface, okay? But our idea in this paper now is using our class, the normal forms in the first work, and we association asymptotic BDE, okay? Because we use the normal forms in the first work, for we have some asymptotic BDE association of the F, okay? So, but we use for this the results of Farid, Davdov, and Blues, Fletcher, Tari, so many authors for classifying our normal forms correspond to topological BDE. But here we use it only at parabolic and the umbilical points, because in that case more important things happens, okay? So, but also we would like to study the flat nodal curve. But flat nodal curve is given by from inflections of the asymptotic curves. So, topological BDE, we lost informations about inflections. Okay? Now we need to use another approach. Now we need to take transversal families of our classification, the first work. After that, we use some criteria did from Kentaro-Sagi for criteria for looking for flat nodal points, and it's possible you draw some examples of the flat nodal curves in these transversal families. Okay? And use, of course, the results of Farid. Farid uses the transversal families here, association BDE. It's possible we draw the parabolic curve also in the same works of Farid. For that, we present some explicit examples of bifurcation diagram of parabolic and flat nodal curve for two parameter families of surface. Okay? Let's go. We divided this presentation in 4 steps. First, we give some notations about binary differential equations. After that, we association the binary differential equation. For short, I say only BDE, okay? And association of families of surfaces in P3. After that, we present the transversal families of the surface classified in the first work. We present the transversal family of these guys. And in the final, we present some examples of bifurcation diagrams, the parabolic curve, and the flat nodal curve for 2 parameter families. Okay? Here we present some examples, but so interesting. Okay? Now, binary differential equation, we have this relation, okay? And we have delta. Delta is b squared minus a times c. If delta is positive, we have 2 foliations which are transversal to each others. And if this delta is 0, we have the discriminant curve. And we know in the discriminant curve, the integral lines, we have cusps. Okay? So having so many results about classification of germs of BDE or families of the BDE, I sit here some data, Davidov, Cibrario, Bruce, Tari, Fletcher, and others. And for instance, only some results about this. If ABC is not vanishing the orange, in some works call this BDE the type 1, but here we don't say the difference about this, okay? Here we say only BDE. And in the works of Cibrario, if the unique direction is transversal, the discriminant, then the BDE is equivalent at this normal form. Equivalent here is possible is topological, smoothly, and diffeomorphic. Okay? In Davidov works in 1985, if the unique direction is tangent to this discriminant, we have this. The BDE is smoothly equivalent at this guy. We have this normal form where lambda is different of 0 and 1 over 16. And that point have one name is the folded singularities. If it's possible, you classify this point topologically using the values of the lambda, okay? We have a saddle if this lambda is negative. This lambda is between 0 and 1 over 16, one node, or one focus if this lambda is greater than 1 over 16. For BDE classification, the BDE codimension 1, codimension 2, and one parameter families of the BDE, two parameter families of the BDE, we have the topological classification, these guys, and that works. Okay? No, now, this is only some comments about binary differential equation. Now, association these results with the surface in P3, okay? Now, we consider our surface given by the Monge form. We know it's possible to divide the surface in three regions: elliptic, parabolic curve, and hyperbolic. And we know having two asymptotic directions, elliptic region, one asymptotic direction, parabolic region. Also, it's possible to divide the umbilical points on the surface that any tangent line is asymptotic. And in that guys here in hyperbolic, this is in the parabolic, we have one field of the pair of directions. The integral lines, these guys, we have the asymptotic curves. Okay? We have asymptotic curves here, but it's possible association these guys with solution of this BDE. Okay? And this BDE is correspond, we need the normal form of the surface. Yeah, of course, here we know that the discriminant curve of this BDE is equal parabolic curve. Okay? So, in first work, we classified by projective transformation these normal forms. Okay? And these normal forms is important in this BDE. So, let's take each class we classified here and the association or correspond the asymptotic BDE here. Okay? In this work, I don't present something about the first work, okay, about classification, because Yutaro in afternoon talk about this in his presentation in afternoons, okay? And I don't talk about this, central projections, here. Here we have our classification for normal form F, okay? Let me explain this table. Here, these results here is did from Platanova or Landis, okay? And a study of the contact surface with the lines, the tangent lines. And here we put the table only in the parabolic points and umbilical points. Umbilical points happens here and here, okay? And this table only parabolic and umbilical. In the first part of the table, this case is genetic. After that is no more genetic, but this classification, this part of the table is for one parameter family of surface. Okay, and here, two parameter family of surface. So now, for each class we take here, let's go see which guy correspond asymptotic BDE. Okay, for the red color I put here, that guy, using some criteria of classification of the BDE, it's possible association these guys at this normal form where the direction is transversal to the parabolic curve. Okay? And go back the table and take the normal forms in the blue color. That guy here is one cusp of Gauss, okay? And the asymptotic BDE association, these guys will have this normal form, classified by Davidov, and lambda here depend of alpha, okay? So, alpha here is different of 0. If alpha is 0, we have this normal form. This means we have codimension higher, codimension now. But in this case, look, our lambda, if this guy is 0, this lambda is negative. If this lambda is negative, we have one saddle. Okay? If this term is 0, don't change nothing in our asymptotic BDE, okay? And now go back here in the alpha. Alpha is equal 1 over 4. This lambda is 0. We have more degenerate case of the BDE. We have the BDE, the codimension 1. So if that guy is 1 over 4, we have this normal form. Okay? Let's now association this class the normal form for asymptotic BDE. So for these guys, I put the color red here. And if we take this normal form, PV1, it's possible this guy is topologically equivalent a non-versal A3 transition with non-Morse type 1. We have this normal form classified by Bruce, Fletcher, and Tari. So here, if we consider this normal form, look, the Hayek function, that guy have one singularity A3, and the parabolic curve have singularity Morse. Okay? In another case, we have these guys look by the Hayek functions, we have A4 singularities, and that guy is topologically equivalent the folded saddle node type, classified by Bruce, Tari, and Davidov comments about this also. And we have this normal form. Okay? And in that case, the parabolic curve is smooth. And another case, this case is umbilical case. This normal form is the A4 singularity, and that guy is topologically equivalent bifurcation, the star, this normal form if is plus, and the minus if this guy is one saddle. Okay? Now, we eliminate all the class, rest only more 4 class, 2 parameter families of surface. Let's go to association these guys for BDE. So, in the first case, that guy also is one A3 singularity. That guy is topologically equivalent to the cusp type, classified by Farid, and have this normal form. Here, the parabolic curve have one cusp. Okay? More degenerate here, V3, is topologically equivalent to no transversal Morse type, also classified in Farid. We have this normal form. Here, the parabolic curve has Morse singularity. Another case, we have A5 singularities, is topologically equivalent a folded degenerate elementary type. Here, the parabolic curve is smooth also. We have this condition. These conditions here, I forgot to say, is from the expansion of Taylor of the F, okay? And in this case, is more remarkable because the asymptotic BDE association, this guy is topologically equivalent to one cusp type 2, classified by Oliver. But this normal form don't have codimension 2 BDE, but has codimension 3. So, while our degenerate flat umbilical class, these generically appear in 2 parameter families of surface, its asymptotic BDE is not equivalent to any type of BDE of codimension 2 with classified in Farid, but is equivalent to this normal form. These have codimension 3 in space of the BDE. Here is the first question in my presentation. We don't know the geometric meaning this. Okay? We don't know is the first questions about this. I don't know. We have this gap of the codimension. In the accounts, okay, have this, but the geometric meaning, we don't know. Okay? So, but now we did this, we would like to study some examples of bifurcation diagrams at parabolic curves and flat nodal curves. So, for this we need another approach, and also we need to define the flat nodal points. of flat nodal curve. So, flat nodal curve consists of the hyperbolic points at which one asymptotic line has more than 3-point contact with the surface. Okay? These guys, we have the flat nodal curve, but if you study the equivalent relation of the BDE, that guys preserved the discriminant, but lost information about inflections of the integral curves. Then, the theory of general BDE is really useful for analyzing parabolic curves, but not for flat nodal curves at all. Okay? So, we need another approach. For one parameter families of surface, the study of the bifurcation diagram, parabolic curves and flat nodal curves is did by Uribe Vargas, and we present all the bifurcation diagrams of these guys. Okay? But now, how to obtain some examples of the bifurcation diagram for two parameter families of surface? Okay? One idea is Faridi already studied the bifurcation of the parabolic curve. Okay? In the BDE results. But if for flat nodal curves, the approach here, now we need to study transversal families of the hour class classified in the first work. And after that, we put some criteria of recognition criteria of the flat nodal points. In the pictures of Farid works, we draw the flat nodal curve there. But this is only examples. Okay? Transversal for us, meaning the Monge-Taylor map of here, defined like that, you P on the surface until send to the Q jet of the F. F is the S parameter family. The transversals means the Monge-Taylor map is transversal to the strata of the IT class we classify in the first work. For IT strata is given by in our first work. Okay? So this one or two parameter families induce one family of the Monge-Taylor map transversal to the strata. Okay? So we have this table at parabolic and umbilical points. The transversal families associate each normal forms. Okay? Now, we would like association also these normal forms and BDE, for example, in this case, for one parameter families of the BDE.
I'm sorry, this normal forms is some final jets or up to it?
Jets.
What is this?
Yes. What's your question?
My question is that you write the normal form. Afterwards, just for some finite jet, this is normal form. Or for whom?
Last word.
You have a map.
Yes.
A family of maps. And this is normal form, the parameter normal form. It is just for finite jet, say for 5 jet or something like that.
Yes, into this jet. Into this jet, like in our classification. You classify jet by jet, only that. Projective transformation, okay? So, yes, this transversal, we don't know, we can't say about is versal or not, okay? We don't have one study for versal, transversal here. But in these normal forms, in that sense of the transversality, using these normal forms is possible association the one parameter BDE and use some criteria of Tari, Blues-Fletcher Tari, and Bruce-Tari. It's possible we association these guys for versal families of the BDE. Use criteria of Tari, except for this case. Because this case here we have only two parameters and the BDE association, this guy have codimension 3. Of course, this guy is not versal. So, let's go to draw our flat nodal curves in the pictures of Farid. But for this we need the recognition problem. One flat nodal point is characterized as the point at which the central projection along the asymptotic line is of type swallowtail or worse. Okay? Have some criteria about this. It's did by Kentaro Sagi. If we consider the projection along the y-axis, we have two parameter deformations like that. And if we consider lambda is determinant of the differential of f, and eta, the vector field, the origin which expand kernel the differential where lambda is equal 0, parabolic curve is given by for these three equations, and flat nodal curve and these three equations. Okay? Here we have in the sides work, but also it's possible to see this in Kabata's works 2016. So let's go for the codimension 1 cases. Okay? Here we confirm the bifurcations of parabolic curve and the flat nodal curve by direct computations using family of the Monge forms in our transversal classification. For example, in this case, we have flat nodal curve have these parametrizations and parabolic curves like that, and we have the same results C and Uribe Vargas. Okay, here we have the phenomenon 8, the flat nodal have 8, we have the transitions, the Morse type, Morse elliptic here, hyperbolic, and again here appear elliptic. Okay, in the same works we lost 2 points here, 2 saddles here, these transitions, and here the umbilical case, same things happens also in the works of Uribe. Now let's go to draw some examples in codimension 2, okay, bifurcation diagrams using our transversal classification. So parabolic curve, Farid also did this. Okay, now we put some new branches in these pictures of Farid. Here, in that case, we have a A3 singularity. This picture is did from Farid, and we have the cusp type of the parabolic curve. We obtain the flat nodal curve have one cusp here, and we have these draws of the flat nodal curves here. Appear the figure 8 here and here. The new branch is here in the number 7. We have the tangent, self-tangent of the flat nodal curve. For this normal form here, appear, I don't put in this work because I have in the first work, because this phenomenon happens in hyperbolic region. Okay? Same thing is happening this, only change the signal. Here, I explained more details. That case, let me first here, we have Morse singularities of parabolic, and the flat nodal have one cusp, 5-2 cusp. Okay, and we have in this branch 2 happens the class of classified, we have the class Didi from Uribe Vargas, we have the transitions of the Morse type here, and happens some phenomenon, we lost this point, we have this in the strata 4. After that happens something in hyperbolic region, the flat nodal curve have this phenomenon, also classified in the first work, and continue this. Again, we have in 8 the same phenomenon in 2, but in opposite case, we have Morse transitions of parabolic, and appear the number 8 here for flat nodal curve. Up here, these guys disconnect. Here, another phenomenon happens in hyperbolic region, and disconnect this point. After we lost this point, okay, in 12, and again, we lost this point again, and go 2-2 type, okay? And this is also easy to analyze. For umbilical case, for codimension 2, is more remarkable because in this case, the bifurcations, this example of the bifurcation is new. We don't use more the results of Farid. So we take our normal form, we obtain the parabolic curve. Also, it's possible we obtain the flat nodal curve, but the expression is so big, I don't put here in slides. But analyze the strata, the singularities of the parabolic, we have one cusp. And analyze this, we have this branch, t equals 0, we have the umbilical case, the codimension 1. In this parabola, we have this case, the parabolic curve have Morse type, okay? And we have this picture. Here in the origin, the parabolic curve have one cusp, the flat nodal curve have one cusp, and two branches smoothly cross in this point, okay? So, in the three branch here, the branch 3 have one self intersection of the flat nodal curve. After that, we go the branch 4, the parabolic have the transition of Morse transitions until 6. 6 we have one star umbilical case and goes here, and between 7 and 8 we need one self intersection of flat nodal curve, but appear two branches in that case. And continue here, now that guy is one saddle, the parabolic have one saddle, and continue until this guy. These guys, we have two cusps here, and we lost this guy, two cusps of Gauss for 2 until 3, and 12 until 13, okay? And for 13 until 2, we have self-intersection of the flat nodal curve. We have two branches about this also, okay? In the case minus, it's similar, but more simple, okay? And this, okay? It's the reference, thank you, and feliz cumpleaños.
Questions or comments?
Just to comment.
Yeah.
That is already the next step. The formulation of my results in that text is wrong.
Oh, really?
Yeah, because it does not account the resonance case. You wrote that always when we have tangents, generic tangents, it has this normal form. That is not so. Because
Okay.
the resonance case was specified here with reference to Rosalis, and it has another normal form.
Okay.
The second one, relating the all elementary singular points, not only saddle node, this is the first in this case. The smooth classification, not topological, but smooth was obtained with this Laura Bobadilla, who is also from here, from me.
Okay.
And so, and you mark that it's just topological normal form obtained by Farid.
Okay, yes, Farid is topological normal form.
But there is smooth normal form.
Okay.
No questions?
Just to complete the information in the part where there is the bifurcations of the flat nodal curve, you can put the limit, the volume of the A.
Okay. Here? Okay.
One parameter.
One parameter. Okay.
In the right, we have the self-intersection of the fractional curve.
Yes.
This point has an analog in the elliptic domain,
Okay.
which will be the self-intersection of complex conjugate fractional curve, but it becomes a real point.
Yes.
So in the left part should be a special point,
Yeah.
elliptic node, which is the analog.
Yes, yes.
So in these points happens the bifurcation.
I see.
To have this bifurcation, you need this special point in the elliptic domain.
Okay.
And then one more thing is that if you take in space-time the picture, you start with an elliptic point, special.
Okay.
Then the boarding of the A will bring with the umbrella.
Really?
And this the self-intersection is a self-intersection with the umbrella.
Okay.
The handle of the wooden umbrella is made by the special elliptic point.
I see.
So in all these cases, in the elliptic domain, was an elliptic point. So an elliptic point of this special kind is replaced by the self-intersection of the fractional curve.
Okay.
And then all these bifurcations can happen
In these forms. Okay.
in the place where before was either an elliptic special point or a self-intersection of the fractional curve.
Okay.
This is the first of to complete.
Yes, yes.
And in the four cases, we got in the space-time with the umbrella. In these four cases.
I see.
And the next thing is that it should be a distinction in the fractional curve. You have two branches.
Yes, yes. I don't put in this approach. Only you have together branches.
The other right.
Yes.
This is very important because you have self-intersections which are stable.
Yes.
But if you don't take into account this, you have other self-intersections which are not stable.
Okay.
They are stable when you are left and right. But if you have self-intersection of right and right, it's not stable. And
I
it
see.
destroys the self-intersection.
I see.
So an observer looking self-intersection cannot distinguish why sometimes it's stable and why sometimes it's not stable.
Okay. This is important. Yes. Yeah.
It's stable only when they are of different kind.
Okay.
When it's the same kind, always unstable. So it's just so it's important this is
Okay. Thanks.
After that, I think, any other comments?